Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to be looking at matrices that have columns that are orthonormal vectors and then look at their inverses. So in this topic we will define and consider something called a permutation matrix. We will then try to determine the inverse of such permutation matrices. We will introduce the concept of the transpose of a matrix. We will also consider real matrices where the columns form an orthonormal basis. And again, we will try to determine the inverse of such matrices. All right, a quick review. Recall that a collection of vectors is said to be orthonormal if, first, any pair of different vectors in that collection are orthogonal to each other. That is, the inner product between the two vectors is 0, and each of the vectors has a 2 norm equal to 1. Now, in a vector space R to the n or C to the n, a collection of n orthonormal vectors forms a basis for that vector space. Now, recall that the inner product for complex vectors conjugates the entries of the first vector in the inner product. Now, recall also that an n by n identity matrix has 1s on the diagonal and 0s everywhere else. You will note that the columns of the identity matrix form the canonical basis for R to the n. So here we have our collection of n orthonormal vectors. Now, suppose that we have an n by n matrix where the columns are a permutation or reordering of the canonical basis vectors. So, for example, here we have a matrix P1. So we start with the third canonical basis vector, then the first, then the fourth, then the second. Here's another example, and yet one more. In fact, without dealing with plus or minus 1, if we just consider positive 1, there are n factorial permutation matrices of this form. So, as I just hinted, such matrices are called permutation matrices, but they're not only called this because they are permutations of the canonical basis vectors. Instead, what happens if we multiply a vector by one of these permutation matrices? Well, if you were to work it out, you'd see all it does is permute the entries of the vector. So the entry u1 becomes the third entry, the entry u2 becomes the first, the entry u3 becomes the last, and the entry u4 becomes the fourth entry, at least for this permutation matrix P1. Not only that, what happens if we multiply a matrix by this same permutation matrix? Well, if you work it out, you'll see that the first row ends up being the third row, the second row becomes the first, the third, the fourth, and the fourth row becomes the second row. So what we get is a permutation of the rows of the matrix A. So again, any matrix that permutes the entries of a vector or the rows of a matrix upon multiplication on the left is called a permutation matrix. And the columns will always consist of a canonical basis vectors. Also, there's other properties which you may observe. First of all, each row has one and only one in that row, and each column has one and only one in that row. column. All other entries are 0. The identity matrix is, of course, a trivial permutation matrix. Also, we've seen simple permutation matrices. Specifically, we've seen that the matrix representing the row operation of swapping two rows, that itself is a rather simple permutation matrix. You'll also recall that we found the inverse of that, which is itself. To undo a row swap, we just swap those rows again. Now, here's something that may be a little bit less obvious, but it's not that hard to realize it should be true. The product of two permutation matrix is itself a permutation matrix. After all, suppose we had matrices P1 and P2, both of which were permutation matrix, and we wanted to calculate the product P2 times P1. Well, this is by definition the result of multiplying the vector u by P1, which simply permutes the entries of the vector u, and on this resulting vector, it's multiplied on the left by the matrix P2, which again just permutes those entries again. Consequently, the result is simply a permutation of the entries of the vector u, and therefore there must be another permutation matrix that is the product of the two matrices P2 times P1. Now, the property of a permutation matrix is such that if Pij is equal to 1 in a permutation matrix, then when determining the ith entry of P times U, it selects the jth entry of U. Similarly, when determining row I of P times a matrix A, it selects row J of A. For example, if P13 is equal to 1, then when we are calculating the first entry of P times a vector U, we are selecting the third entry of the vector U. So what is the inverse of a permutation matrix? Well, the first observation we can make is the inverse must also be a permutation matrix, for we must move everything back to where it originally started. Now, given a permutation matrix P, if Pij is equal to 1, then when calculating the ith entry of P times U, we select the jth entry of U. How do we reverse this operation? Well, when calculating the jth entry of the inverse times U, we must select the ith entry. That is, if the entries of the inverse are represented by Qij, then specifically Qji is equal to 1 whenever Pij is equal to 1. Thus, the inverse of each of the matrices we previously looked at include, well, here's the identity matrix, and the only entries that are 1 are on the diagonal, so Pii is equal to 1. Therefore, the inverse is itself. Here's the matrix P1. Well, in this case, 1, 2 is 1, so therefore, in the inverse, P2, 1 must be 1. And we can do that for the rest of the terms. So 1, 2 is 1, therefore 2, 1 is 1 in the inverse. 2, 4 is 1 in P1, therefore 4, 2 is 1 in the inverse. 3, 1 is 1, and therefore 1, 3 is 1 in the inverse. And finally, 4, 3 is 1 in P1, therefore 3, 4 is 1 in the inverse. There's P2 and its inverse, P3 and its inverse, unchanged. Notice that in each of these cases, we are just moving the 1 to the opposite position across the diagonal. So it's a reflection through the diagonal. Consequently, any entries in a permutation matrix that are already on the diagonal remain on the diagonal. So the process of reflecting each entry in a matrix through the diagonal is actually a process that is called taking the transpose of a given matrix. And if the matrix is A, the transpose is represented by A superscript T. So in this case, taking the transpose of this full matrix, well, 12 is on the diagonal, so it stays there. However, 2 and 4 are flipped. So negative 4 goes into entry 1, 2, while 2 goes into the entry 2, 1. We also flip the entries negative 1 and 3, the entries in the corners 0 and 5, the entries 7 and 4, 0 and negative 6, and in the middle 8 and negative 3. So again, given any matrix A, we can calculate or denote the transpose by A superscript T, and all that is all of the entries in A mirrored through the diagonal. Consequently, if P is a permutation matrix, then the inverse of that permutation matrix is the transpose of that matrix. So this is one case where it is not necessarily necessary to explicitly calculate the inverse as we saw in the previous class. However, if you were, you would still get the same answer. You would end up getting the transpose. Now, recall that the identity matrix and all other permutation matrices are comprised of columns that make up the canonical basis for R to the n. So all permutation matrices are made up of permutations of these 4 canonical basis vectors. What happens if we had a different orthonormal basis for R4, for example? For example, here is a basis for R4. Here's a different orthonormal basis for R4. Remember, the 2 norm of each of these vectors is equal to 1, and in either set, if I take any 2 different vectors and calculate the inner product, then the inner product is 0. Of course, if the 2 norm is equal to 1, then the inner product of each vector with itself must equal 1. So let's create matrices that are formed by taking these orthonormal vectors as columns. So let's try the same thing. Let us multiply the matrix A on the left by the transpose of A, and then we'll try again with the matrix B. So let's calculate A transpose times A. So on the left we have A transpose, on the right we have A. On the right we have 4 orthonormal vectors forming the columns of A. On the left we have those same 4 orthonormal vectors, but now they are forming the rows of A transpose. So when we calculate the first entry, we are element-wise multiplying the first row times the first column, which is the inner product of the first orthonormal vector with itself, so that must equal 1. Next, we want to calculate the entry 1, 2, so we element-wise multiply the first row by the second column, and that is again taking the inner product of the first and second orthonormal vectors. As they are different, the inner product must be 0. However, you can determine that it is also 0 by simply calculating it. To calculate the entry 1, 3, again, we take the element-wise product of the first row and the third column, which is again essentially the inner product of the first and third vectors, which is 0. And finally, to calculate the entry 1, 4, we again element-wise multiply and add, and in this case that must also give us 0. To calculate the second row, again, we're multiplying the second row element-wise by the first column and adding, and because that's the inner product of the second and first vectors, the result is 0. Next, those are the same vector, and so we have the inner product of the second vector with itself. That must equal 1. The inner product of the second and the third vectors is 0, and the inner product of the second and the fourth vectors is 0. Well, we can do the same for the remaining entries. We get the same result by calculating A times A transpose. And if you were to do this, you'd get the identity matrix, and therefore, yes, we see that the inverse must equal the transpose, at least if the columns form an orthonormal basis. We get the same result by calculating B transpose times B and B times B transpose. In the first case, well, you can check yourself, but 0.04 plus 0.16 plus 0.64 plus 0.16 is indeed equal to 1, and the rest are either 1 or 0. And the same if we calculate B times B transpose. Consequently, a matrix that has columns that form an orthonormal basis is called an orthogonal matrix. And there's a nice theorem. A real matrix is orthogonal if and only if the transpose is the inverse of the matrix. If the transpose is not the inverse, the matrix is not orthogonal. If the transpose is the inverse, the matrix must be orthogonal. Consider this matrix in C to the 4, that is the four-dimensional complex vector space. In this case, each entry of the matrix is multiplied by 1/2, and so you'll notice that the entries of this matrix, the first column include 1 raised to the power 0, 1 raised to the power 1, 1 raised to the power 2, 1 raised to the power 3. The second column has j raised to the powers 0, 1, 2, and 3. The third column has -1 raised to the power 0, 1, 2, and 3. And the fourth column has -j raised to the power 0, 1, 2, and 3. Once these are multiplied by 1/2, the columns do form a basis for the four-dimensional complex vector space. Question: if I simply calculate the transpose of this matrix and multiply it by the matrix, do I get the identity matrix? Interestingly enough, the answer is no. And you'll notice that we have to do something else, because you'll remember that the definition of the inner product for complex vector spaces is slightly different than that for real vector spaces. Consequently, we do have to make a small modification after we calculate the transpose. But this is a topic we will look at in the future. So what's the relevance of this topic? Well, calculating the inverse of a matrix can be expensive, and it is potentially numerically unstable. If a matrix, however, is orthogonal, then finding the inverse is easy, and finding it is also numerically stable. Consequently, when we look at future algorithms, we will very often be looking to see whether or not we can include an orthogonal matrix in the result. Consequently, following this topic, you now understand the definition of a permutation matrix. You know that the inverse of a permutation matrix is its transpose. You understand that if the columns of a real matrix form an orthonormal basis, then we call the matrix orthogonal, and the inverse is also that matrix transpose. Note also that every permutation matrix is an orthogonal matrix. You are now also aware that this makes calculating the inverse much easier and numerically stable, and you know that we will be discussing such matrices, including complex matrices, later on in the course. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!